Earlier in the course, at the end of chapter 2, we introduced concepts of discrete dynamical systems, Markov chains, and stochastic matrices. If you need a refresher on those ideas or want to see any of the terminology, I definitely recommend going back and rewatching those videos. In this video, we're going to be looking at how eigenvalues and eigenvectors can help us understand the specifically kind of the long-term behavior of a Markov chain. This will lead to the concept of a steady state distribution. And so we're going to get things started here with an example about modeling exercise habits. So suppose we have a population that we divide into two groups, a group that exercises regularly, which we're going to label capital E, and a group that does not exercise regularly, which we will label as capital N. Suppose we have this information about these populations. Each month, 85% of those who exercise regularly continue exercising, and 15% stop exercising regularly. And then 10% of those who do not exercise regularly begin exercising, while 90% continue not exercising regularly. So we're going to let x sub k be the vector e sub k n sub k, which represents the number of people in each group after k months. So to begin, we want to find a transition matrix A such that x sub k plus 1 equals A times x sub k. And one common thing we might do is to sort of draw a picture with our different states. So we have E, the exercise regularly group, and N, the does not exercise regularly group. We have different sort of percentages of our population that either move between the two groups or stay within their own group. So going back to this information, 85% who exercise regularly continue exercising regularly. So we might put a 0.85 there to represent that, and then the other 0.15 of those that exercise regularly move to the does not exercise regularly group. And then we have 10% who do not exercise regularly begin exercising, so that would be down here, 0.10, and then the other 90% of this group would remain within that group. So if we want to construct our transition matrix A, then we might label our columns. This is going to be a 2 by 2 matrix because we've got two states that we could possibly be in. And so each of these decimals we put up here, each of these probabilities or percentages is going to go in one of these spots. So this 0.85, which is the group that goes from E back to E, is going to go in the first position here. And then the 0.15 will go down here. So each of these components is going to tell us that that is the sort of probability or the percentage of the population that moves from the column to the row. And then we have 10% goes from N to E, so there's our 0.10, and then 90% goes from N to N. So this would be our transition matrix. So 2 by 2 matrix. Here it is written out again. And what we would like to do now that we couldn't do back in chapter 2 because we hadn't learned about these things yet is to find the eigenvalues and associated eigenvectors of A. And I'm not going to actually go through all of the work right now. You certainly could do our determinant of A minus lambda I and solve, set that equal to 0 and solve, and sort of go through all that work. I've kind of done that in advance and found that we have lambda, I'm going to label this as lambda 1 equals 1, and that's going to be our first eigenvalue. And V1, its associated or an associated eigenvector is the vector 2, 3. And then lambda 2 is equal to 0.75, and V2, an associated eigenvector there, is the vector 1, negative 1. And again, you could certainly go through the work. You could plug this into your computer or write a program to find these, or you could kind of just try them out now, right? You could find that AV1 equals lambda1 V1, right? Just to sort of remind us, equals lambda1. Now, lambda1 is 1. So if you were to compute AV1, you should find that it just equals V1. And then you would find that AV2, if you want to try this, would equal 0.75 lambda2 times V2. So that's one way to check once we sort of know what these things are. And we're going to put this to use later. One thing I will remind you is that since we've got two distinct eigenvalues, we can diagonalize A. So let's just write that out now. We can write A equals P D P inverse, where D is the diagonal matrix, 1, 0, 0, and then 0.75, putting the eigenvalues down the diagonal, and P would be the matrix with the first column being V1, so 2, 3, and the second column being 1, negative 1. P inverse, again, something you could compute, which I've already done, is going to equal 0.2, 0.2, 0.6, and negative 0.4. Okay, so we will use this all later on, but just figured while we are looking at the eigenvalues and eigenvectors, we might as well write out our diagonalization of A. And now let's take a look at sort of a little bit more with this example. Suppose that initially we have 1,000 people in a population, all of whom exercise regularly. So, maybe it's January, everyone is determined to stick to their New Year's resolution. So we've got this whole population of people that are ready to go. They all exercise regularly. Then our initial state vector would be x0 equals 1,000, 0. So this again represents the fact that all 1,000 people in our population exercise regularly, and none of them, are in that does not exercise regularly group. So let's look at what happens over time. We could compute x1, the state vector for this population, after 1 month by finding ax0. And again, I've sort of done this in advance, but you are welcome to try it out as well. So if we started with all 1,000 people exercising regularly, after 1 month, we would find that only 850 of them continue to exercise regularly, while the other 150 move to that does not exercise regularly group. And then if we wanted x2, that would be ax1, but x1 was ax0. So ax1 would be a squared x0. And so again, I sort of did this in advance, but you could compute this out. We'd get 737.5 and 262.5. So again, sort of fewer people are exercising regularly, more are in that does not exercise regularly group. The 0.5s, right? So not necessarily saying we have half a person, but that's the exact value. From here on, I'll probably round to the nearest whole number. So x3 similarly is ax2, but we could write as a cubed x0, and I'll just approximate this with whole numbers. This is approximately 653 and 347. And then in general, x sub k is going to be a to the k x sub 0. So we could continue computing powers of a. And we might ask this question: what happens as a goes to infinity? Well, one thing we've seen before is that diagonalization is one way to sort of more easily consider high powers of a matrix. So a to the k is equal to p d p inverse to the k. But that's equal to, and again, we showed this in a previous video, p d to the k p inverse. And what's nice about this? Well, d to the k, since d is diagonal, is just going to be the entries on the diagonal to the k. And sort of furthermore, write this out, one of those entries was 1, and 1 to anything is still just 1. So this becomes p times 1, 0, 0, and then 0.75 to the k, and then p inverse. So not only is one of these entries 1, but the other is a number less than 1. And so when we take higher and higher powers of that number, in this case 0.75, as k goes to infinity, 0.75 to the k goes to 0. So as k grows and grows, as we take higher and higher powers of a, our matrix d to the k is going to become very, very, very simple. So maybe I'll see. Let's continue here. Okay, so as a goes to infinity, we have a to the k will equal p times, actually, let's do it like this. We'll have that a to the k will go to p. D to the k, as k goes to infinity, just becomes 1, 0, 0, 0, and then p inverse. So this really, really, really simple thing. We found p and p inverse previously. So this is going to equal, if we write this out, so p was that 2, 3, 1, negative 1, and then 1, 0, 0, 0, and then p inverse, that 0.2, 0.2, 0.6, negative 0.4. Okay, and this works out really nicely if you go through the math here. Give ourselves a little space. This works out really nicely to the matrix with both columns being identical, 0.4, 0.6, 0.4, 0.6. So as k grows and grows and grows, a to the k becomes this. Now, if we were to take this matrix, this 0.4, let's come over to the left-hand side and use up all our space here. So 0.4, 0.6, 0.4, 0.6 times our initial state vector, we just get 400, 600. And so as k goes to infinity, a to the k x0 goes to 400, 600. And that, if we kind of go back, 400, 600 is actually a multiple of 2, 3, the eigenvector that that was associated with the eigenvalue of 1, and therefore 400, 600 itself is an eigenvector with the, associated with the eigenvalue 1. And it is also sort of what our system will be approaching. So 400, 600, as well as 0.4, 0.6. So the two columns of this matrix that we landed on down here, 0.4, 0.6, 0.4, 0.6, are both eigenvectors corresponding to the eigenvalue of 1. These are what are known as steady state vectors. So definition, if A is a stochastic matrix, we say that that a probability vector, Q, and a probability vector is just a vector whose entries sum to 1. So a probability vector Q is a steady state or stationary vector if AQ equals Q. So notice that Q is an eigenvector of A associated with the eigenvalue 1. In the last example, we would have Q equals that 0.4, 0.6 vector. It is, again, an eigenvector corresponding to the eigenvalue 1, and it is also, interestingly, the columns of what a to the k is approaching as k goes to infinity. And I already sort of did that. So find the steady state vector. So I already kind of stated it here. It was that 0.4, 0.6. But I want to look a little bit more at, maybe why that happened. So if we, again, sort of consider that a to the k equals p d to the k p inverse, then as k goes to infinity, a to the k goes to this p 1000 p inverse. And this 1 is, the only thing that was left here. And that came from the fact that it was an eigenvalue, right? And so this 1 was an eigenvalue, and the rest of these, in particular, this became a 0 because the other eigenvalue here was a value less than 1. And so this was an eigenvalue, which we called lambda 1, and this was sort of that lambda 2 to the k as k went to infinity, but lambda 2 was less than 1. So that ended up going to 0. And so, this will always be the case if we have a situation where we have an eigenvalue of 1 and, another eigenvalue if we have a 2 by 2 matrix, or the other eigenvalues if we have a bigger matrix, that are all either, somewhere between -1 and 1. So have absolute value less than 1, or if they're complex, then there's another way to think about this, but essentially go to 0 as we raise them to higher and higher powers, then this will always be the case. Okay, and so this is going to lead into a really powerful theorem. We say, first of all, that a matrix A is called positive if either A or some power A to the k has all positive entries. And if that is the case for a stochastic matrix, so if A is, this now is the Perron-Frobenius theorem, if A is a positive stochastic matrix, then the eigenvalues satisfy lambda 1 equals 1, and the absolute value of lambda j is less than 1 or j greater than 1. So just to sort of really highlight exactly what's going on here, this is first of all saying that if we've got a positive stochastic matrix, then it is guaranteed to have an eigenvalue equal to 1. It happened in this example we just did, but this will always, always, always be the case. Not super hard to prove for a 2 by 2 matrix, a little bit trickier for larger matrices, but something that can be proven for a positive stochastic matrix. And the other piece is that the other eigenvalues will all have absolute value less than 1. And then, when that is the case, we're going to always be in this scenario where as k goes to infinity, a to the k is going to be approaching this p d to the k p inverse, but d to the k is going to approach a very, very simple matrix with just a 1 in one of the positions and 0 is everywhere else, which will ultimately lead us to the steady state vector q. So the rest of this Perron-Frobenius theorem says that this means that A has a unique positive steady state vector q, and every Markov chain defined by A converges to q. And so the Perron-Frobenius theorem tells us that every positive Markov chain has a unique long-term equilibrium. No matter where the process begins, it eventually settles into the same steady state distribution. So this is a really, really powerful theorem. If you can model something as using a Markov chain, then all you have to do to sort of understand its long-term behavior is compute its eigenvalues. Well, actually that one of its eigenvalues will be 1. So really all you have to do is compute its eigenvector corresponding to lambda equals 1, and then find the scalar multiple of that. So it's still an eigenvector that will be a probability vector. So, going from the eigenvector we found, so, just to really make this clear, we found V1 was 2, 3. How could we turn this into a probability vector Q? Well, Q, we just want to make sure that the sum of these values is equal to 1. And so we could scale this, since 2 plus 3 is equal to 5. We could scale this by 1/5. So Q would just be 2/5, 3/5 to guarantee that the sum is 1. So that's our 0.4, 0.6. So when you have a positive stochastic matrix, if you want to know sort of the long-term behavior of it, then just find an eigenvector corresponding to the eigenvalue of 1, which you know will be the case by this theorem, by the Perron-Frobenius theorem, and then scale it to make it a probability vector. So a pretty powerful theorem that gives us a lot of insight into what the long-term behavior of a stochastic matrix is going to be.